All right, welcome back, everybody. Couple of orders of business first. I sent an email out on, I don't know, Friday? Was it Friday? I don't know. One of these days before today. I sent an email about the exam and the exam on Wednesday. And I went ahead and I chose the problems I wanted on the exam. Right now it's sitting at 15 problems. I took the exam. The way I did it is I picked a problem that I liked. I would do the problem. I would time myself, and then I just kept track. It took me 55 minutes to do all 15 problems. What's that? For me, yes. So I think it might be a little too long, so I'm going to trim it down. I think just a few problems. I would be guessing there's going to be 12 problems. And, you'll have the hour, 40 minutes. Wait, sorry. Yeah, 1 hour, 40 minutes of a regular class. I did say you are allowed to have a single 8.5 by 11 sheet of paper with formulas, steps, procedures, no worked out problems, okay? You can't even have on there like x squared equals 4, x equals plus or minus 2. I mean, that would be a worked out problem. Nothing can be worked, all right? With me on that? Steps and formulas and things like that. I mean, anything to help guide you, but in no way you working out something ahead of time and using it as a reference. Okay? And I'll check them. I'll check them that day. But there's a lot of different formulas that I don't necessarily think it's important that you memorize everything. So you just find what you think is valuable, put it on a sheet of paper. You won't be allowed your differentiation formulas or integral formulas, but I'm also not going to be asking you to do complicated integration or differentiation on this test. So, you know what I'm saying? You don't need your table of integrals, like secant cubed. Yeah, you don't need the reduction formula for secant to the n or anything like that. I'm not going to. That was for the take-home stuff. Okay? All right. Be on time, because if you're late, you only get until what? 2:40. That's when the time cuts off. So if you walk in at 2:30, you've got 10 minutes. Now, of course, if something happens, you let me know ahead of time. You can use your calculator with cross product. Don't be programming all these things into it that are like, you hit program and it brings out a big old 40-page, reading of all the notes and worked out problem. I mean, if you want to invest that much time into that, but all right. Okay, so we had been talking about maximum minimums, and I hope that you attempted to do problem number 4. I hope that you've tried that already. Was it 4 on the take-home test? Was it 4? I think you could do 4 now. I hope you've worked that out. Oh, it was 3? Okay, 3. Never mind. 4 is the closed interval. So I hope that you were able to do that and work through it, and that maybe you did the homework for that part of the section. But we got to finish off 11.7 today. And what we had started talking about was trying to find the maximum minimum of a function on a closed bounded set. We talked a little bit about what a closed bounded set was last time. And then I said that in your notes, I have these examples, and I have them worked out with all the steps, right? Maybe you should read through those. Well, instead of me sitting here just reading this out and going through it, I decided I'd make up a problem to start class separate from what's on the notes. I'm just going to make up a new problem and then do that one. Then after I do that, and hopefully you get a feel for how things work, I'll come back to this and then walk you through these, and hopefully it'll make more sense then. Okay? Questions? Yes. Yes. They're in the book. Yeah, I put them in after I'd handed those out. Anytime you see that with the light blue and the text, that's usually out of the book. Okay, so real quick before class, I threw something together. Let me see if this will open up for me. Let me write down first what I want. Let me write the problem down. Ooh, there's the mini exam. Where's today? Can you believe we're, yeah, what is this, day 12? The 3rd of March? I don't know. For this class, I'm not sure how many there are. Feels like halfway. I'm not sure. Did I ever tell y'all why I only give midterm and final? To stress you out? It's because we need class time. We need time for lecture. If we had like 3 or 4 exams, I mean that's 3 or 4 days we can't cover material. That's why I only do midterm and final in here. All right, here's the problem. And I seriously just threw this together like 15 minutes ago. So let's see how this works. All right, so let's find the absolute maximum and minimum values of f of x, y equals 2xy minus 1/2 in parentheses x to the 4th, y to the 4th, sorry, plus y to the 4th, plus 1 on the triangle with vertices, corners, right? -1, 0, 1, 2, 2, 0. Now that's the way the problem would appear on a test. All right. It's still 11.7. Yep. All right, so the difference between this problem and what we had done last class is that we're being asked for the absolute maximum and minimum. So I had made the analogy last class that in Cal 1, you find the absolute max and min of a function on a closed interval. That's the first thing you ever do. And then you go and you find it on an open interval. And I said closed interval was harder closed interval was easier in Cal 1 than open interval was. But in Cal 3, closed bounded set is harder than just finding the local max and min. So how do we find local max min? What do we have to calculate? All that. So we can calculate D, right? We use that second derivative test. But if you're on a closed bounded set, which we are because we are looking only over a triangle, then everything changes, all right? So what I did is I threw together some code that will illustrate. Is this the one? No. And again, bear with me, I just put this together. There's the triangle, right? That's our domain. It has the vertices -1, 0, 2, 0. Is that what I had? Just double check this. 1, 2. Okay, so that's our domain. We are restricted to that closed bounded set. Imagine taking every point in that domain and mapping it into the function. And then you get part of the surface, right? Not the whole surface, you get part of it, and we call that a region. So to the right over here, actually here. There's the surface, okay? There's our surface. Trying to get top view of this. It's kind of tough to see. But can you see from the top, there's our triangle on the ground, right? We're mapping just those points into that surface. Now I'm going to show you the region we're talking about here. It's just that greenish part. And I think what I'll do is I'll pull the surface out so you can see it. And all we have is the region. There we go. Does that make sense? Visually, does it make sense? You got the triangle. It's mapped into the surface. Just over that triangle, whoa, you get this. And if I pull this appropriately, whoa, should be able to look straight on top of this. And you can see that some of the points in the domain come up, right, above the XY plane. Some of them go below, right? So I want to find the absolute max and min of this. Can you, oh shit, what the hell happened there? Well, when in doubt, reevaluate the cell. There we go. Can y'all see where some of them are? What does it look like we have here? Absolute min down here, this corner. Absolute max somewhere up there, right? Now it appears that the absolute minimum occurs when we plug in this corner, 2, 0, right, into the function. It looks like that's where we get our minimum, right? So you would say that the minimum, absolute minimum, appears from our picture to occur when we're on the boundary of our closed region, right? So our minimum is on the boundary. But the maximum, which looks like the top of this hill here, right, appears to occur where? Inside the bounded set. Which means that to attack the problem, we have to look at two things. We have to look at, first of all, is there a max min inside the region? And then we have to look around the region, around the edges. And what you're guaranteed is that if you have basically a continuous function on a closed bounded set, that it will achieve all its absolute maximums and minimums on the edges or within the boundary. Somewhere it's got to achieve it. With me? Okay, now it's time to go about this. So the first thing I'm going to do now, and remember, we have to act like we don't have the picture, right? The picture's just there to help us see what we're trying to find. But going back to this, if we have no picture, our first thing, first order of business, is going to be find the local max mins. Now, I'm not concerned about saddle points at all. Okay, saddle points don't matter because I'm not asked for saddles, am I? I'm asked for the absolute max and min. So how do we find local max and mins? Compute D, right? Compute D. So that's everything we did last time. So I'm going to go about that. First thing here, I'm going to compute fx. So what's the derivative of that with respect to x? 2y. Then what's the derivative of what's inside that parentheses with respect to x? So all the y doesn't matter, so you should get what? Minus 2x cubed. All right. That's the derivative with respect to x. What's the derivative with respect to y? I'll do it in blue. 2x minus 2y cubed. All right, so we've got that. With me? We need to know when these are 0, right? Or when these are equal to each other. So I think what I'll do is I'll take the first one, I'll set it to 0, which means 2y minus 2x cubed must be 0, which means that y must be x cubed. right? I can do the same thing for the other equation, or for the other partial, set it equal to 0, and I should get x equals y cubed. Right, just manipulating things, moving things around. And then what I can do is I can take my first equation here, and everywhere I see a y in this equation, I can replace it with what? X cubed. So this equation becomes x equals x cubed cubed. What's x cubed cubed? X to the ninth. And then we have an equation that just has x in it. So move things to one side. Remember, don't divide by x, right? Move everything to one side. I'll move everything to the right, but then I'll flip everything over. X squared minus x is x to the ninth minus x is 0. Then what? Factor out an x. X to the 8th minus 1 equals 0. X is 0. And x equals plus or minus 1. Now, whatever x is, right, y is that cubed, isn't it? That's what we have here in the yellow. Y is x cubed. So let's get our y coordinates right underneath these. If x is 0, what's y? 0. If x is 1, what's y? 1. If x is negative 1, y is negative 1. So we have these potential critical points, right? Critical numbers is what we call them in Cal 1. These are critical points to us now. We have the critical point 0, 0, 1, 1, negative 1, negative 1. And what are we going to do at those points? What are we going to do with those? Calculate the d, right? Second derivative test. But, yes. What do you mean? Okay, yeah, okay, I know what you're saying. You have to be careful because you're using kind of with what's happened on some of the problems we've done. If x is 0, that doesn't mean you can let y be 1 and y be negative 1, because if x is 0, I know that then y has to be 0. Because of the equations force things to happen. Yes? I know what you're talking about, because we did an example where you said, what were the different combinations? All right. Any ideas on what we can do? I want to come back up here and draw a quick picture. Where were my vertices? It was at negative 1, 0, 2, 0, right? And 1, 2. So I had vertices here, here, here. I never drew my triangle, but which of these points that I just got live inside that region or on the boundary? 0, 0, and 1, 1, right? 0, 0. I don't like that color. I'll use green. 0, 0, and 1, 1. Yes? Now, let me rephrase something because I think I misstated something. I said, what are we going to do with these points, right? And we said, calculate D. That's what we would do if we were trying to find the local max and local min, right? What we know here is that if there is a local max, right? If there is, and if there is a local minimum, it would occur at one of those 2 points, right? One of those 2. For us, we don't care about whether or not it's a local max or a local min. All we care about is what's the value of the function there. So it's all we're going to do. I think the better analogy would be go back to Cal 1. If I'm trying to find absolute max and min on a closed interval like this, we found out where these points were, right? But then did we do a second derivative test? No, we took those points and we plugged them into the function, didn't we? And we compared it to the endpoints. That's what we did in Cal 1. That's the same idea here. We found the critical numbers, those 2 points. We found them. We don't care about calculating any second derivative test on them because all we want to know is what happens when you plug those into the function. And then we will compare them to the endpoints. But for us, we don't have endpoints. We actually have what? The boundary of the region. Okay? So come back here. All I want to do, I'm going to come back down to this. I'm going to scratch out -1, -1. Why? It's not even in my region, so I'm not going to consider it. But what I will do is I will take this point right here and I will plug it into the function and then figure out what I get. I think I get 1, right? That's my function. When you plug in 0, 0, you get 1. Okay? What happens when you plug in 1, 1? You get 2 minus 1, right? What do you get? 1, 1, that's 2, half of that, -1. So you just get 2, right? 2 minus 1 plus 1, right? Right here. Plug 1, 1, 1, 1. You get 2 here. Half of 2 is 1. Take away 1, add 1. It's gone. You have 2 up there. So 2 is what you get out, right? Okay, now all we're going to do is we're just going to keep these handy, all right? And remember those for later, all right? Now here's where things get new. This is the new part of what we have to do, and that's today's. What we're going to do is we're going to come up, I'm going to redraw my region on a different page for you, but now we're going to attempt to look at the boundaries. So here comes my new page. Come back here and erase this junk. All right, my region looks like this. And I would recommend you draw a good region. Take your time with it. Okay, my region is basically made up of 3 line segments, isn't it? Three line segments that connect these vertices. And so what I'm going to do is I'm going to look at each one of these line segments one at a time. So I'm going to move along one of the line segments, see what happens to the function, move along another one, then another one. So I'm going to label them, and it doesn't matter what order. I'm going to call this first one, since it's a line segment, I'm going to call it L1 because it's a line. Over here, this one, I'm going to go clockwise L2, and then over here, L3. So I have 3 lines, don't I? What I want to do is imagine, let's go with L1 first. Imagine that you're going to be moving along L1. So imagine you're picking points on L1, anything on that yellow highlighted part. The question is, what does every point on that highlighted line look like? So what does an x coordinate look like, and what does y? So let me just pick an arbitrary point here. I know that point has some x value, right? So the x coordinate is x. But what's the y coordinate? Well, it lives on a line, doesn't it? And lines have equations, right? All I have to know the equation of a line is its slope and its y-intercept, don't I? Y equals mx plus b. So what is the equation of this line? Well, what's the slope of that line? Looks like we went up 1 over 1, up 1 over 1. So the slope is 1. So y equals 1x. And then what was the y-intercept? 1. So plus 1. That's basically x plus 1, isn't it? So that means that if I plug in some x value, what's the y value then? It's the x plus 1, right? So I'm going to come back to this point over here, and I'm going to put the y coordinate as x plus 1. Do you agree? The x is x, the y is x plus 1. That will give you the points on this line. However, we also need to make sure that we stay on that line and don't go past it. It's only a line segment, right? So it starts somewhere and ends somewhere. So what is my restriction on x? -1 to where? 1, right? Right there. X can go between here and here, and that'll draw the segment. So I'm gonna do this down here now. I know that all my points look like this: x, x plus 1, and I know that x must be between -1 and 2. No, not -1 and 2, -1 and 1. Any questions? If you're moving along L1, every point looks like x, x plus 1, and your restriction on x is between -1 and 1. So now let's take that line segment and let's imagine mapping that line segment up into the function. When I do that, I'm taking the x and y coordinate and plugging them into the function. Right? Like that. Which will be, now you have to break out your function and replace all your x's with x's, so just leave them alone, and all your y's with x plus 1. So I get 2x times x plus 1 minus 1/2 x to the 4th plus x plus 1 to the 4th plus 1. Right? That's what I would get. Which equals 2x squared plus 2x minus 1/2 x to the 4th minus 1/2 x plus 1 to the 4th plus 1, right? Now I've started cleaning things up a little bit, but let's try and get our heads around what we have here. This right here only has one variable in it, right? So we can look at that right there as a function from Cal 1, right? It's a function of a single variable. And it has a restriction on its domain, so I have a restriction on a closed interval, right? I would like to know the biggest and smallest this ever gets on that interval -1, 0, -1, 1. So you're going to basically be applying the closed interval method for a Cal 1 problem right now. Now your function that you're looking at, your Cal 1 problem, is a 4th degree polynomial, right? And so we need to take the derivative, right? That's how we do this. We take the derivative, we set it equal to 0. That'll give us the critical numbers. What do we do after we get the critical numbers? Plug them into the original function, and then also plug in the endpoints. The biggest is your max, the smallest is your min. So derivative, I think I'm ready for this. What is the derivative of that function? 4x plus 2 minus 2x cubed minus 2 x plus 1 cubed. That's it? That's all? Okay. And now we'll have to set it equal to 0. Do you agree with me, though? Yes? Any questions? All right, so this is equal to, let me see, 4x plus 2 minus 2x cubed minus 2. How do we expand that, y'all? Ever seen that before? Okay. If you had to cube that, that's what you would get. And then distribute through. Pascal's triangle. Oh. Pardon me? If this was a minus, that's right. Yeah, that's if that was a minus. Oh man, we just got our asses saved right now because those 2's canceled. Right? Those 2's canceled. That really helps out a lot because I have to set this equal to 0, don't I? All right, so let's set this equal to 0. If the derivative is 0, that means I'm going to set, let me get this in order here, negative 4x cubed minus 6x squared, then minus 2x equals 0. Y'all just let me know. Like I said, I made this problem up. I haven't worked through it, so if you see any obvious mistakes, let me know. I'm just going to scale everything by negative 2. Scale everything, divide everything by negative 2 right now. 2x cubed plus 3x squared plus x equals 0. Right? How can you solve that? Factor out an x. What's left is 2x squared plus 3x plus 1. Oh, does that factor also? 2x plus 1, x plus 1 equals 0. Are you kidding me? That worked? I did not think it was going to be that clean. We got really lucky here. I don't think the next one's going to be this clean. Because we're only going around L1 right now, right? I'm pretty sure when we get to L2, it's going to suck. And L3 might be bad too. But are there any questions as far as the method? Still not there. What are our 3 solutions to this? 0, negative a half, and negative 1. All right. Now what I need to do is I need to take those values, right? I need to plug them into the function here, and I need the endpoints. What were the endpoints? X was negative 1, right? And x was it 1 or 2? It was 1, right? Okay, I'm going to just put here endpoints. Do you see that one of our endpoints actually overlaps with one of our critical numbers? So you don't need to do it twice. I just want to point out, here are your critical numbers from the derivative being 0, and then here are the endpoints. We plug those values into the function. But what function? Well, you have choices. You can go all the way back up here. Where is it? Wait, well, it's not on this page. Never mind. The original function, or this was the one we were trying to maximize right there, right? That's it. That was the Cal 1 problem. Just plug x in right here, and you'll get your results. Now, what it really turns out to be is, like when we plug in 0 here, what I would write is 0 what? F of 0, 1 would be equal to, now plug in 0 for x here, and what do you get? Careful with this one right here. Right? 0 there gives you 0 plus 1 is 1. So that's negative 1/2 plus 1. So you get 1/2, don't you? So you get 1/2 here. What's f of, let's see, if I plug in negative 1/2, then my y would have been 1/2. But plug negative 1/2 into here. And what do we get? Let's see if we can do it. 1/2 squared, or negative 1/2 squared, 1/4, and then times 2. 1/2, so I have 1/2, and then what? Plus, minus 1, remember, because we're plugging in negative 1/2, right? So my negative 1/2 right there, that gives me negative 1. Negative 1/2 to the 4th, 1/16, times this, negative 1/32. And then, what about here? Negative 1/2 in here, plus 1 is 1/2 to the 4th, 1/16, then times half, negative 1/32 again. Plus 1. Plus 1 minus 1 cancel. Say again? Where did I get what? Oh, just right here, right? If this is negative 1/2, add 1 to it is positive 1/2. So that's 1/2 minus 1/16, 7 negative, or 7 positive, 16. So multiply. I'm just doing all this. I'm expecting you could do that, right? 7/16. Y'all happy with that? No? I mean, you do agree with the computation? Okay. 7/16. Now, let's plug in negative 1. Negative 1 squared, so that's 2. 2 minus 2 is gone. Negative 1, doesn't matter. So minus 1/2. And then that's 0, right? And then plus 1. So you just get 1/2. Pardon me? That was nice? Yes, I agree. I don't have to do it again. What's f of 1? Or sorry, what happens when I plug in 1 for x? It's 1, 2. So you get 2 plus 2 minus 1/2 minus, what's that? 2 to the 4th, right? 16 divided by 2 is 8, so minus 8, and then plus 1. 4, negative 4, negative 4 plus 1/2, negative 4 plus 1/2, right? That's what I've got. That's 4, 8, this. Okay, I got everything there. What's that? Negative 7/2. Questions? Which of these is our max? 1/2, right? So where does it occur? Okay. At 2 places, right? At the 2 endpoints, right? I have the same value. And then the minimum value happens at what? 1, 2. Pardon? These are all, well, I got to go back to our region. Where was 0, 1? 0, 1's here, right? That's 0, 1. The next one was negative 1, 0. That's here. And then the other one was 1, 2. So it looks like we have something, we have our maximums are here, and our min is here. So our min's happening, our actual minimum is actually happening here, right? And our maxes are happening here and here. Now let me go back to our picture. Try and bring this. I'm going to try and spin this around. Do y'all understand we're looking like here's L1 right here? I'm trying to turn this, and just so we can see that one edge. I don't know. Can you all see that? Here's negative 1, 0. We go up, it's at 1/2. Then it comes down, then it comes back up, and right here, halfway down that line, goes back up to 1/2. Then it starts dropping, and it comes down to negative 7/2 down here. At the end point, it's down here. Do you see that? It's kind of cool, right? For L1, 2, and 3. Yes. Well, yeah. Yeah, that's what we have to do. Well, I picked a problem that's not very friendly. The ones that you should work. Well, let's look at this next one's a little bit harder. The L2, it's a little harder to get the line from. See what we get. Is everyone ready to move along L2? What we're going to do is, when we're done, we're going to look at what we got originally, which was, remember when we did this earlier? We did the partial set them equal to each other, and we found those points there. We said, let's hang on to those for later. We're going to wind up comparing those to what happens on L1, to what happens on L2, to what happens on L3. And out of all of those, the biggest one we get is our max, and the smallest we get is our min. But we have to go all around. This is it. This is it. Well, you know, that's what I had partway handed out the other day. Or no, I was going to hand it out, I never did. I'll hand it out right now just so you can see it real quick. What's that? Yes, you'll have a problem like this on the midterm. But the L1, L2, L3, L4, whatever it is, that's all I have. Are there any extras? That's all I brought. I don't know where the others went. Huh. Well, y'all can share. I'll just look off yours. So this is just Mathematica, the program I use, the code. This was to calculate D. Well, no. What was I doing here? Well, look at the first line, input 13. I define the function 8xy times square root, blah, blah, blah. Does that look familiar? Oh, no, we're going to do this today, actually, this problem. So I define the function. Then I take the derivative with respect to x. That's input 14. Then I simplify. I have the computer simplify it for me. And then I take derivative with respect to y. And then I have it simplify it for me. And then look at input 18. Solve the derivative of f with respect to x equals to the derivative of f with respect to y. And the derivative is 0, both of them. And solve that, and x is greater than 0 and y is greater than 0, and do that for x and y, and it spits out the two solutions. And then, what do I do next? Oh, in input 20, I take f, and then you see where it has like a, what is that called? The leaned over, huh? Not that, backslash is the other way. Front slash? Forward slash period. Do you see forward slash period? That means replace. So it says take the function f and then replace x with 2 square root 3 and replace y with 1 over square root 3. So those are my two answers, right? From the line above. Replace it into the function, I get 16 over root 3. And then the last line just turns it from exact to decimal. Anyways, that whole problem I was able to, I typed that up in probably like 30 seconds, you know, I mean, because I'm used to it. Just there you go. There's a whole problem done. Didn't have to do any algebra at all. It's just done. All right, that's pretty nice. All right, back to the joy of this. We're doing that problem later. Let's go L2. All right, let's talk about L2 as far in terms of its, you know, it's a line. Right? It has a slope. It has a y-intercept. Maybe the slope's easier to get. What's the slope of that line? Down 2 to the right 1, right? So negative 2. So I know negative 2x. What's the y-intercept? So I actually have to try and go backwards to get up to the y-intercept. Can I? Right, down 2 to the right 1. That means up to the left 1. Would that put me on the y-axis? Yes? And what would that be then up there? 4? Okay. Now, what if it didn't line up that way? Like, what if it really just didn't work out that clean, where you could tell? Well, I expect every Cal 3 student that if I give you 2 points, which you do have 2 points, right? That if I give you 2 points, you can find the equation of the line through 2 points. And that's something I ask in my 310 class. 310 is like developmental math, right? So you should be able to recover the equation of a line through 2 points if needed. But this one works out real quick. Y'all follow? +4? I already don't like this because I know where that's going to get plugged in here in a second, and it's not pretty. So if I pick a point on here, it looks like x negative 2x plus 4, doesn't it? You see what I'm saying? Yeah. So let's go to L2. Also, what's the domain restriction on L2? My x is between 1 and 2. Between 1 and 2. What do they call that? Trial by fire? This problem is like trial by fire. I'm giving you a pretty extreme example, but they're all the same. You got to move around the edges. The problem here is going to be plugging this into our function. So what is, on L2, was I in green? Green was L2. L2, all my points looks like x negative 2x plus 4, and 1 was less than or equal to x is less than or equal to 2. That was my domain restriction. Now my function evaluated at that point, or those points, should be 2x times negative 2x plus 4, right? Minus 1/2 x to the 4th plus, now here's the bad part, negative 2x plus 4 to the 4th plus 1. Oh, close my parentheses. All right, not good, right? So I'm going to create a new notebook real quick, show you how this works. F is defined to be 2x times y. I'll make this bigger so you can see it. What was it? Minus 1/2 x to the 4th plus y to the 4th plus 1, right? Okay, I've defined f. Now I want to take f and I want to replace my y's with what? Negative 2x plus 4. Okay, there it is, right there. Now I want to take the derivative of that answer. If you just put percent sign, it'll take the last output, that's your new input. Derivative of that with respect to x, right? Is that, okay? Now I want to set that to 0, right? Solve what I just got equal to 0 for x. Oh. Reals. No, it's all right. It's all right. Well, that's actually encouraging, because if it can't be set equal to 0, then it doesn't have a critical number, which means that it's always decreasing or always increasing, which means that the endpoints are where you're going to have max and mins. So, but hold on, let me just verify. So I'm going to run through it again. Do that, replace here, solve that in the reals. Not happening. Reduce. Evaluate notebook. Okay, so it does not appear that there's a real solution to that, which means we have no critical points. Now, trust me, I would never give this problem to you on a test, all right? I'm illustrating the point, okay? When you get to these on the test, when you do your F, it's going to be quadratic. It's at the most cubic, and when you take the derivative, it'll be at most quadratic. And everyone should be able to solve a quadratic. So just keep that in mind, all right? So no solution. Now, let's go back to the picture. Where's my picture of this thing? Come here, picture. I'm moving along that back edge, right? Where's the back edge? I've lost myself here. I don't know if I agree with that. Do you? To me, it looks like on that back edge we have something, right? It comes up and it comes back down. Yeah, let's go back. There might be something wrong in this. Minus 2xy plus 1. What? What's wrong? That negative goes through here and here? They just put a -1 inside. I trust Mathematica more than myself sometimes. 2xy, I'm replacing y with this. That's pretty straightforward. Let me try this. I would find it very difficult to believe that Mathematica could not solve that cubic equation. So maybe there's something else in here. Place that derivative of that with respect to x, right? Reduce that equal to 0. Simplify. Let's see what the derivative looked like simplified. Yes. Okay. There, there, there. Cubic, it's a cubic right there. I'm not quite sure why it's not giving an answer here. Okay, let's try something else, since this is technology, right? Let's have it graph this. And what will we be looking for? I'm just going to plot this. What was our restriction on x? It was 1 to 2. The only thing I can think of is maybe my picture isn't right. Well, we have some options here. We can keep investigating this, or we can just wave our hands at it. What do y'all want to do? Or is it which side? This side right here? This edge right here? No, because that has curvature to it also. Yeah. What do y'all want to do? You want to do it by hand? You want to keep going on this? I don't know. We did type in -2x plus 4, right? When I did that? Replace this -2x plus 4. How about if I just take this right here, -2x plus 4, and then over here just replace it. That way we're really sure that it's not just something in my was plus. No, but sometimes the input's a little weird. Okay, does that look exactly the same? Well, not exact. Well, yeah, it is, right? It is. But now what I can do is I can take derivative of f with respect to x here. It's the same. Hmm. I'm a little stumped on this. If I graph this, this is what I get for trying to give you a weird example before class. If I graph, there's the cubic there, right? Just on a wider interval. Yeah. Graph F, plot F. Okay, maybe, yeah, because it could turn out that it was 1 to 2, right? Okay, I'm graphing F. That's not encouraging, right? Because it does look like it has a max there. Okay, there's only one other option I have here. I don't know why Mathematica is not pulling that. Let's see if this free program called WinPlot can do it. What I'm going to do is I'm going to have it, what was it, 2x times negative 2x plus 4 minus a half times x to the 4th plus negative 2x plus 4 to the 4th plus 1. And I want to do it only, I'll just go negative 5 to 5. Pen width 2, 3. There it is. And now I will have it do extreme measures. Boom, there it is. X is 1.36. 1.36. Yeah, but there's something else happening there with Mathematica. I'm not sure. I'll look into it and let y'all know what it was. Like why it wasn't doing that. Uh-oh. Interval, we want it from 1 to 2, right? Okay. See if that, does that kind of look like what we had? Zoom out, page down. Okay, there we go. All right, you see that right there is supposed to be that one side that we were saying it looked like that edge. I'm convinced that is that edge. I think I know what it might be. Hold on. No, X is X. I don't want to waste any more time on this. What was the value? What was the value? 1.36? 1.36. We'll go with that. That lives in our interval, right? All right. It's not very often that WinPlot saves my ass, but it did apparently in this one. Okay, 1.36. So we go down through here. We say f prime equals something. We got it. F prime equals 0, and that meant that x was 1.36. Now what I need to do is evaluate the original function at the endpoints, which would have been 1. And then what would happen if I plug 1 in here? 1, 2. What happens if I plug in the other endpoint? What's the other endpoint? X is 2, which means 0. And then at the critical number we just found, 1.36, and then comma, negative 1.43? Yeah, okay, good. Let's plug them in. And we're plugging them into what? This, right? Now, do I trust Mathematica to do that for me? Yes, of course I trust Mathematica to do that. Okay, let me do this. I'm gonna have it do f replace x with 1 negative 7 halves. Replace x with 2 is next. -7. And then we replace it with 1.36. 1.42. 1.43, we'll say. Okay? So we have a minimum -7 and a maximum of 1.43. Disaster. Now we need L3, right? Yeah, L3 should be easy. L3 is more like what you're going to see. L3, what can you tell me about every point on L3? X is something, right? And Y is 0? X is something and Y is 0, always. So you don't have to find an equation of a line or do any of that. So it makes things nice. I think I'll do it right here. So on L3, all points look like x0 on what interval? And we go all the way from -1 to 2. So now I just need to know what happens when I plug in 0 for y to the original function. -1/2 x to the 4th plus 1. That's what I get. Now derivative. Are you all right with that? Plugging in 0 for y, it kills off a bunch of stuff. Derivative of that, I like that derivative. It's what, -2x cubed. Set that to 0. Means what? X is 0. So I just need to check what points. Ready for, what are the endpoints? -1, right? -1, 0. Then 0, or I'll do them in order. Endpoints, and then I'll do the critical number. It doesn't matter. 0, 0. If you go back and look at everything, I think we've actually tested all these points at some point earlier. At -1, 0, what did we have? Someone look back in their notes. And at 2, 0, didn't we just do 2, 0? 2, 0 was -7, right? What was it at -1, 0? 1/2? And then at 0, 0, it's 1. So here I have a minimum here and a maximum here. All right, let's put it all together. Summary, okay? From the local min-max from the very, very beginning of the problem, which has taken us over an hour to do, what did we find was our max or min? What was it? It's at 1, 1, and it was 2. So let's look at it as an ordered triple. We had 1, 1, 2 was our max. What was our min there? Or we didn't have one? 0, 0, 0? No, 0, 0, 1? That's what I'm talking about right there. We had 0, 0, 1, and then 1, 1, 2. So 0, 0, 1 I need to put on my list. 0, 0, 1. That was a min. Okay, then what about on L1? On L1, what was our max? Did anybody write down any of this? Wait, what was the max on L1? 1/2, -1/2, and then what? -7/2? Wait, y'all are confusing me. 0, 1, 1/2 was the max on L1. Okay, thank you. and then minimum -7, right? What else? L2, 20, -7, and then we had the 1.36, 1.43, 1. Whoa, 1.43, something like that. And then on L3, what do we have? 207, -7, which we already have, and 001, which we already have on this list. So which of all of these is the biggest we have? Max. Right there. That's our absolute max. It happens at 1, 1, and the maximum value is 2. What about min? Here and here, right? It didn't look like it on my picture, did it? Which one? Oh, -7 halves. Okay, I just misheard. Good. That makes me feel better. That wasn't all for a wrong answer. Okay, this one right here should be -7 halves, like that. So this is those two constitute our answers. Okay, this is an absolute minimum. This is an absolute maximum. Yeah, that was up there. So in our picture, which I'm going to revisit that later. In our picture here, our absolute max happened at the top of that, right? And that was at 1, 1, 2. And then the other one happened at this corner edge, and it was at what? 2, 0, -7. It's a lot of work, right? Okay, now let's go back to my notes. Oh man, I'm gonna have to save this. Throw it on my desktop real quick. Come back to that. All right. So now let's take a look at this problem. Now you should have these in your notes. It's all worked out. So we have a function f of x, y equals this. You have a triangle. So what I have to do first is, by using this triangle here, I need to determine what the equations of the lines are, right? Now, would y'all like me to come up with those equations, or you want help on that? Let me help you, but I'm not going to draw it on there. I'm just going to do it over here. Unless my other program. Okay, what are these points? What is it? 1, 0, 5, 0, and 1, 4. Okay. Now, if I call this, what did I call it in my notes there? What was that left side? L1. L1's the bottom. Okay, so L1's the bottom when X can be X. So this is L1, L2 is here, and L3 is here. So when you're on L1, what do all the points on L1 look like? All the points look like an X coordinate and then 0. And what's the restriction on that? You're on the interval 1, 5, right? What about on L3? Let's do L3 because it's easier. All the X coordinates are 0, all the Y coordinates are just some Y. What's the restriction on Y here? See, because you're going up and down on L3, right? Your Y goes from where to where? 0 to 4. So Y is between 0 and 4. And now L2 is the one that's a little more interesting. I think I'll erase that interval over here and just put 1 less than or equal to X less than or equal to 5. Okay, so if you're a point on this diagonal on L2, your X coordinate is X. What's the equation of that line? Well, what's its slope? This is 4. So down would be what? How much do you go down? 4 and over 1 to 5, right? So down 4 over 4. So slope is -1, right? Down 4 over 1, or down 4 over 4. So negative X, and then what's your y-intercept? Yeah, the y-axis isn't on here. This is a weird way this drew. Here's your y-axis. It comes up like this. So it's the slope being -1 is down 1 over 1, down 1 over 1. So you can go up 1 over 1, which would put you at 5. So X plus 5. What's the restriction here? X is between 1 and 5. All right? Any questions on that setup? I usually think that's like the hardest part of the whole thing is the setup. Can I erase this, or do we have any questions? All right, let's move on and look at the rest of this problem here. So the first thing I did is I find partial with respect to X, partial with respect to Y, figure out when they're equal to each other or equal to 0. So that's me doing that part for local max-min, right? I find a point 2, 1. I plug it into the function. I get an ordered triple there. So I'll compare that later. Now L1, all I have to do is plug in X and then 0. That gives me this. Look at this rinky-dink thing. I mean, we were just sitting there trying to work that problem with mathematics. We had a 4th degree polynomial. Look at this example. You get a linear function. And then you don't even need to really find the derivative, but you can. The derivative is -1, which means that there is no max-min. All you have to do is check the endpoints. So you plug in the 2 endpoints, and you get 2 points, and you use those later. Does this make more sense now? I mean, if you've looked at this before and you're like, huh? Or does this make sense what we're doing? Okay. Now if we're doing L2, we do this. We plug that into the function. We get a quadratic. We take the derivative of the quadratic, right? We get linear. Set it equal to 0, you get a solution. And then you plug that in, and you plug your 2 endpoints in, and you get 3 points, which we will compare later. Then you go along L3. Oh, ooh, no one caught this. The x-coordinate wasn't 0, it was what? No one caught that. Back to your picture up here. It's because of that damn drawing. Sucks. Remember, the y-axis is right here, right? So any point off this, go back and fix this, off L3, the x-coordinate is what? 1, and the y-coordinate is y. This is the y-axis, so you have to come out 1. Your x is 1. Yes, domain. Well, domain goes. Yeah, hold on. No, domain will be different. The domain will go from 1 to 5 instead of 0 to 5. Because oh wait, no, 0. We use y. Y between 0 and 4. Okay. So when you plug those in, right, you plug in 1y into the function, you get, again, a linear. You take the derivative, it's constant. Plug in the endpoints of the interval, you're done. Now you bring everything together. You compare everything that was boxed earlier, all of them, and you'll get 2 places where you have a minimum, and then you have 1 place where there's a max. Why isn't it all? It's not letting me see it. Is it on your page? Oh, there it goes. It's cutting it off the bottom. And then you have 2 places where you have a max. So what's the minimum value of this function on the region? -2. Where does it happen? At 2 different places. What's the maximum value? 2. Where does it happen? At 2 different places. And I had shown you in class last time, you know, how you can bring this region here, and you can look at it. It's that green region right there. There are your 2 max points. There are your 2 min points. Okay, let's look at the next one. Look at the region here. All I tell you is x is between 0 and 3, y is between 0 and 2. So that basically creates a rectangle. All x values between 0 and 3, y values between 0 and 2. That gives you this. So you're going to have L1, L2, L3, L4, right, to go around there. But they're all going to be pretty relatively easy. Let me see how I labeled them. L1 is x and 0. So I did, let's see, what did I do here? L1 was here. L2 for me was 3y, which was this one. I must have gone counterclockwise here. So do y'all see now from the notes? Moving along to L1, your x can go between where and where? 0 and 3, and then the y value is stuck at 0. So x0 is what the points look like. And your x is between 0 and 3. Now what about L2? Now your y value can change up and down, but your x is fixed where? 3. So your points look like 3, your y's are free, but your y is stuck between where and where? 0 and 2. And then you can continue to go all the way around. Y'all think y'all can figure out the rest? All right, let's move on. If we actually did work through that one, let's just see on L1. On L1 we would have, when we plug it in, we'll get a quadratic. We take the derivative, set it to 0, check the endpoints. We wind up having only 2 places. I'm just trying to see if there's anything interesting. Are all of these turn out to be nice? See, on L2, we have a linear function, so when we take the derivative, it's a constant. On L3, look at on L3. We turn out having a quadratic. Take the derivative, it's linear. Set it equal to 0, we get a number, and then we plug in the endpoints. Okay with that? On L4, it's linear. Take the derivative, it's a constant. So you just check the endpoints. And then you compare them all together, and you get your absolute max and min. And I also did at the very beginning, I did the partials. Set them equal to each other, set them equal to 0. It could be cubic, because then when the derivative, you get quadratic. Yeah. I won't ever, no, not on the test or something. I won't make, yeah. Like the one I gave you earlier? Yeah. No, I wouldn't do that to you. Now, we have the quadratic formula. That's why I'd always expect you to be able to solve a derivative that was quadratic. There is a cubic formula, but it's very tedious. Let's look at this one. Find the absolute max and min of this function. On the region, D equals all the points such that your x is bigger than 0, your y is bigger than 0, so what quadrant are you in? First quadrant. And x squared plus y squared is less than or equal to 3. Well, what's x squared plus y squared equals a number? That's a circle, right? Radius with certain radius to it. So from that, you have to discover, I guess, or know that you're talking about first quadrant, talking about a circle with radius square root of 3. Right? Because it's x squared plus y squared equals r squared. So if r squared was 3, that means r is root 3. So I know that this is root 3. So tell me about, let's see, how do I do L1 here in mind? L1, I'm guessing, is the x-axis part. Yeah. So I called the bottom here, I called that L1. And then I called it L2, although I shouldn't have called it L, because L we've been reserving for line. You could say C1 or C2, or just call it L2. It doesn't matter. L is just the different pieces, right? So y'all are okay with me leaving it as L2? No one's going to get upset about that? L3 here. So would you agree L1 and L3 are pretty straightforward? We've done enough of those. L2 is the only one that causes some trouble. So just remember that if you live on this, right, you have an x coordinate, and your y coordinate must satisfy the equation that was given to us. And I gave us x squared plus y squared had to be equal to 3. So if you solve that for y, you get 3 minus x squared on the right. Then take the square root. Now, I'm supposed to do plus or minus, but what? Yeah, in the domain, the region I'm talking about, your y has to be positive. So that's why I only look at the positive one. So that means that the y coordinate is the root 3 minus x squared. Thank you. What's the domain restriction here? 0 to what? Where does the x starts at 0 and ends where? Root 3. All right, I'm going to move through this here now. So I do the derivative. What happens here with the derivative? I take the derivative, fx, fy, and look at what happens. If I set these equal to each other, turns out, look, if you look at both of these, if I let y be 0, right? If I let y be 0, won't it satisfy both equations? Remember that bonus problem I gave you? Some of you did? This is similar to that. If you let y be 0, then it doesn't matter what x is. Okay? Doesn't matter what x is. And so that means that the critical points we have can look any of them. There's an infinite number of them. They all look like this. Any point that has a y value of 0 is a critical point. And therefore, these are all the boundary points, right? This is on the boundary of our region. All these points, x0, isn't that bottom edge up there? So we will determine the maximum when we investigate that boundary. So that's what I'm saying here, is that it turns out that our boundary turns out to give us some information about local maximum, but we're going to investigate it later. So that's why I address it later. There I go on L1. When I plug in this, I get 0, which means that it's always the same, isn't it? The function's constant, which means it doesn't have a max min. It's always 0. 0 is the max, 0 is the min. Same thing. If I go on L2, I have to plug this in. Things work out real nice. You get a cubic. You take the derivative, and it's quadratic. Setting that equal to 0, you get these values. You get plus or minus -1. But then, because of where you are, you can only take the positive one. Then you plug in, you figure out your critical numbers. Endpoints also. Then on L3, it's pretty straightforward. You get, again, you plug in 0y, you get 0. That means the function's constant anywhere along that edge. So this is kind of an interesting problem because you have a maximum that occurs at a certain point, but your minimum value is 0. But it happens all along 2 of your boundaries. So the way you answer that, I mean, look at the way I answered it here. x0, 0, and 0y0 are the form of the points representing the absolute minimum of the region. And that means, like, when you go up and look at this region up here, anything along this front edge here or this edge back here, the region was always 0 along those edges. So any point on those edges would constitute the absolute minimum where it happens. The minimum value is 0. Absolute minimum is 0. But the max happens up here. Okay. How are we doing on time? 10 minutes? Okay, let's see if we can at least start this one. Now this says that I think in your notes it says do example something, right, in the book, or do problem. Okay, it's wrong. That problem doesn't match up with the book. In fact, they took this problem out of the book, or at least I can't find it. So in the new edition, find the volume of the largest rectangular box with edges parallel to the axes that can be inscribed in the ellipsoid 9x squared plus 36y squared plus 4z squared equals 36. So you have an ellipsoid, right? Ellipsoid is like a big egg. And you want to put a rectangular box in that ellipsoid. And you want to find the maximum, volume. Find the volume, the maximum volume of a rectangular box that can be placed in this ellipsoid. Now, this problem can be done using Cal 1, but we're going to investigate it as a Cal 2 problem instead. Everyone understand at least the question? I've got a picture here inside. I've got a rectangular box sitting inside of an ellipsoid. Do we know what inscribed means? Inscribed means that the corners touch the ellipsoid, right? Those corners, the edges of the box inside touch the edges of the ellipsoid. All right, let's try and attack this then. And let's see. I have it written down here so I don't have to refer back. The ellipsoid was 9x squared plus 36y squared plus 4z squared equals 36. That's the ellipsoid, and we need to maximize the volume in there, right? Okay, so let's talk about three-dimensionally We have a box, right? A rectangular box. It's going to have some dimensions to it. If I call, let's say, if I go out a certain distance, let's call that x, and then I go out a certain distance on the y-axis, y, and then I go up a certain distance up here like that, z, right? Then if I form a box out of just this, so I draw that back, I go up, come over, this. That box right there lives in which, or where does it live? In the first octant, right? That's in the first octant. Now the box that we're trying to inscribe into our ellipse would have this one, the one behind it, the one going around, and the ones below, right? So imagine going backwards, we would have another box like this. Then below. You get the idea? What I'm trying to do is figure out a formula for my box in terms of x, y, and z, because my ellipse is in terms of x, y, and z, right? So what is the volume of that total volume of that total solid there? It's x, y, z times 8, isn't it? So isn't the volume of a rectangular box, as pictured there, 8 times x, y, z? Yes? Now, if I do that, the volume, and I want to find the maximum volume, well, you can let x, y, and z be anything you want, right? And it starts changing the volume. The problem is we have to be inscribed in the ellipse, which means there are some restrictions on the x, y, and z. They have to satisfy that equation up top, don't they? So what I'm going to do now is I'm going to take the equation up top and I'm going to solve it for any one variable that I want. In this case, I'll just choose z. So take the equation up here, solve it for z. I'll go ahead and divide out 4. I don't know why I did that. That? Yeah. I wish it was a 4 there. 9/4 x squared. And then square root. So z is equal to square root. Now, do I need plus or minus? No, because z, in my picture, z is positive. 9/4 x squared minus 9y squared. So in order to live on an ellipse, your z value has to be the square root of 9 minus blah, 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 blah. Yes? Now what I'd like to do is I'd like to take that z and I'd like to plug it in here. Right up there for z. And then if I do that, my volume becomes this. My volume will only have 2 variables in it, won't it? So I'm going to call it v of xy. Instead of just v, I'm going to stress to everyone that volume is now a function of 2 things. It's 8 times x times y times z, but z is 9 minus 9/4 x squared minus 9y squared. All we have to do now is find the maximum of that. Right? That's a function of 2 variables. I want to know its maximum. The question now becomes, am I trying to find the maximum on its domain, like just calculating d, like we did before, or is this on a closed bounded set? Is there a restriction on x and y here? Remember, you have to live inside the ellipsoid, right? So your x, y values have to be somewhere, right? They have to be restricted in somewhere. Or maybe it doesn't even matter. What if you were to go into this and say, just calculate D? You would find local. What do you think you would find? Think you'd find a local min? Think you find a local max? X and Y are restricted to be greater than 0 right now, aren't they? So I know that I have to live in, I guess if I'm looking like that little yellow part, but that lives in a region, right? X can't be, well, you have to look back at the ellipse. Go back to the ellipse. If you smash the ellipse down to the XY plane, what's the equation? You smash it to the XY plane. The Z is gone at 0. What is that? What's the equation? 9x squared plus 36y squared equals 36. It's an ellipse. It's an ellipse. So what I will do, because I'm not going to be able to finish this, is take that handout I just gave you again, right? Look at that handout. Just refer to that. The one that there wasn't enough that I did on the computer. So you see the first input was the function. I defined it 8xy square root 9 minus 9 x squared over 4 minus 9y squared. And then I differentiated it, right? Then I simplified it. Then I differentiated with respect to y. Then I set them equal to each other. And I only got one critical point, right? What was that critical point? 2 over root 3 for x and 1 over root 3 for y. Yes? Now, let's think about this logically. If x were 0, right, the volume of this would be 0. If y was 0, it would be 0, right? So the minimum that this thing could ever be would be 0, wouldn't it? If you let x or y be 0, the volume is 0. Does it make sense that if you start letting x get bigger and y get bigger, all it can ever have is a maximum? I mean, it doesn't make sense that you would have a minimum other than 0 itself. So it would be logical to think that that point reasonably could only represent our maximum, right? So you don't have to do a lot of work because there's a geometric picture behind this. Start letting x get bigger and bigger and bigger. Then if we only have one critical number, it must represent the maximum. Can't represent the minimum. Yeah, so what happens is the volume, I actually have it in that picture here. So here's my ellipsoid, solid ellipsoid, and then inside I've got a box. And look I have the computer is calculating the volume for me, okay? Right now I have an x value. I'll drop these open so you can see what the x values are. Oh, it's actually I have it preset to start at the maximum. This is the maximum volume right there. X coordinate is 2 over root 3, y coordinate is 1 over root 3. The volume I get is 9.2376. Now if I start moving my x, what's going to happen to volume? It's going to get smaller, no matter what happens. See? See, what happens is if x gets bigger, it gets longer, but it gets shorter, right? If x gets smaller, right, it gets taller, but it has to become less depth to it. So there's an optimum somewhere in there, and that's what we've found. And y is the same thing. I can change it in the y direction. Ooh, see, I went to an infinity there. Ooh, my program didn't like that at all. Okay? So this is, that doesn't look right. What the hell is that? I think just showing a rectangle in there, just an arbitrary box inside there in the first octant. And then there's the whole, all 8 of them together. All right, well, we have a test. I at least finished 11.7, okay? I thought today we might get into 11.8. That one stupid example I did kind of messed things up. I hope, though, that by me going through that, you saw just, again, it's the process. It's the method of going along the edges. I'm going to look right now at what, because I already did the test. The problem that I did on the test that was closed bounded set took me 10 minutes to do. So, non-Mathematica, no. I'm looking here, quadratic, quadratic, quadratic. They're all quadratics. So, I'm sorry? On chapter 10, how many problems? Oh, I can't tell you how many problems are on each one. I can tell you I have 15 problems on, I'm going to pick from these 15. And I actually think I already know which ones. What I'm trying to do is get it down to where the test took me about 40 minutes, and then you have 100 minutes with it. So you should take a little bit more than twice as much time. Keeping in mind, these are not like take-home mini-exam problems, okay? These are pretty straightforward. So what things did I say to look at to get ready for Wednesday? Your homework and the chapter review. When you look at the chapter review, you know, if I were looking at a chapter review, you can go, you don't have to hang out and listen to me, but if I were looking at, let's say, chapter 10's review, which is on page, and just the exercise, not the true and false and all that, just exercises, like chapter 10 is page 612. Let me see. Number 4, calculate the given quantity. So you're given 3 vectors and you're asked to find 2 times the vector plus 3 times the other. Cross product, dot product. You think I'm going to ask you that? No way. Okay, I'm not going to ask you to calculate a cross product. Okay, now as opposed to something like this, find the distance from the origin to the line, and they give you the parametric equations. That's more like it. It's something that you would have done on your homework, but it's not something like you have a line going through the intersection of this and the center of a sphere over here, and find that it's not like the take-home stuff, but it's, you know, it's along the lines of what would be in here. An athlete throws a shot at an angle of 45 degrees to the horizontal with an initial speed of 43 feet per second, blah, blah, blah. I never even really did anything like that. I wouldn't anticipate you doing anything like that. So, all right. You don't have to have what? Oh, quadratic surfaces? No. No, you do not need to know, like, this is the paraboloid of 2 sheets or something like that. You don't need all that. Nope. Wait, hold on.